Namaskar my dear friends. Let us try to understand what is non-invasive blood pressure monitor, and we'll also understand what are different specifications, how we can design the schematic for a blood pressure monitor design. Okay. So basically a lot of manufacturers are there. These days medical device manufacturers are producing NIBPs not only for the hospitals but also for the home applications. So it is now very become popular for the home usage also. Okay. And it becomes very handy because it is a portable device. It can be utilized by any like a person which is there at home, and if you want to monitor your blood pressure uh, on a daily basis, it will become very handy because you don't want to always visit the doctor, right? So in this we will try to understand what are the different features that should be there, what are the different specifications, and at the same time we will understand how we can design the schematic. So it will be very beneficial for the engineers who are trying to design NIBPs or any other kind of like schematics for this purpose, so that they can be kind of an expertise in the hardware design schematic. Okay. So actually it looks like this. There will be a cuff that is connected on the hand of the person, and it goes to the pump, right? So this pump tries to like fill the air which is connected through a valve, air valve. So if you see from the WHO, that is World Health Organization, they have also released a document like what are the different like categories of blood pressure monitor and what are the different specifications. So if you see, we have blood pressure monitoring device. There are two kinds. One is non-invasive, that is there will not be any piercing inside the body, okay, and one is invasive, that is called direct device. So invasive, basically they will be utilized only in the doctor's place like hospitals and all, and we will not be talking about this at all. Okay, our aim is to talk about non-invasive, and non-invasive can be of manual analog that was earlier being used with mercury sphygmomanometer. Okay. Same way, these days we are going to utilize automatic a lot. Okay, so automatic we will have semi-automated cuff, then automated cuff, then cuffless. All these technologies are there. So we will try to understand about semi-automated as well as automated cuff. So these are the two like target device that we are going to design. So why don't we do one thing? We'll try to understand different specifications that we should put as a design requirement, and once we do that, then it will become much easier to complete a block diagram using that. Okay. So if you see, we have to have a display for displaying the systolic, diastolic pressure as well as like the pulse rate and all. So you can utilize one 3.2-inch LCD which will be a character LCD. If you want, you can give a backlight to that so that it can be utilized in night time as well. Okay. Then there will be NIBP range. Okay, so this range can go up to 0 to 300 mm of Hg, and based on your manufacturer requirement you can put the like accuracy as well. Let's say plus minus 8 mm of Hg up or down. This is maximum. Okay. Now the pulse rate you will try to design with, let's say 30 to 180 bpm, like beats per minute, with plus minus 5% accuracy. Okay. If you want for your better design capabilities and all, you can vary this particular like tolerance values, let's say 4%, 2%, or even if you want to go worse, then it can be taken as 10%. Okay. We'll try to give memory as well, because like let's say you have some 4 users in your home, so all the 4 users can like find out their blood pressure ranges, blood pressure values, and last 30 readings of each one of them can be stored. So total 120 readings can be stored. These days if you want, you can like you have very good memory devices like EEPROMs and all are there, so you can store as high as, let's say 1000 values also. So it all depends upon requirements and features that you want to put with your device. Power, since it is like a portable device, so we'll try to power it up through alkaline batteries. Okay, so 4 alkaline batteries we can put, so 4 into 1.5, that is 6 volt will be there, or otherwise you can utilize 6 volt adapter also, or we'll try to give one of the like USB pin also. So through your laptop USB you will be able to like do that, which will be giving you 5 volt output. Okay, there will be a cuff requirement which will be 22 to 35 centimeter arm cuff, which is used for like adults. Okay, and app connectivity can also be given, like let's say you want to connect it through a app, healthcare app, so that whenever you measure the value, that value will be displayed in your mobile phone as well. Okay, and this is how you can connect it, or you can connect it through Bluetooth as well. So all those functionalities can be given. It can be auto power off. Let us say you measured your NIBP and you kept the device as it is, so after waiting for around 1 minute or maybe 5 minutes you can keep it off. So it all depends on the software that will be done during the design. If the battery level will also be keep on checking, so we will give all these features in our software design, and at that time we can give a low battery indication as well, like battery voltage level is lower. That all depends on like circuit design capabilities, like how you are going to design, whether you're going to have an ADCs for checking the battery level and or not. Okay, we will have error indication also, like whether pressure sensor is working properly or not, air valve is closing and opening properly or not, the monitor is starting and like monitor voltage is proper, motor voltage is proper or not. We will have Bluetooth capabilities also, or if you don't want to have a Bluetooth, then simple design will be enough. Okay, so the design what we are going to try is we'll be having a target of very high in design, which will be meeting almost all the IEC standards that is required. Okay. Okay, so more things if you want. You will have a temperature range of operating is 10 degree centigrade to 40 degree centigrade. We will try to keep. So we will have a testing complete from 10 degree to 40 degrees environment temperature range, and the device should work completely okay. Okay, so this is how we actually try to define each and every parameters. You can see the storage temperature range also. If you want, you can put it. I am just giving you an indication. These ranges can vary always. Okay, so this is not the fixed values. So this is I am showing you for the like example purpose, and actually these are actual accurate readings. Okay, so you can directly take these readings, or otherwise you can decide by yourself. So storage temperature I have put it -20 to 55 degrees centigrade. If you want, you can go ahead, let's say -15 to let's say 70 degrees centigrade also. Okay, now connection detection we will have cuff detection, like once cuff is connected, then we will try to like show the device that yes, cuff is connected. We will have operating mode, as I told you, it will be semi manual, like manual mode as well as automatic mode, right? More features, we will have IHB detection, that is irregular heartbeat detection. So since we are giving the pulse rate values, then we can understand what is the like irregularities in that heartbeat. So that also we will try to detect and show them that your heartbeat is irregular. Okay, like if the heartbeat is quite higher compared to the normal values of 70 bpm, then you can show it that it has IHB, or if it is lower, like let's say less than 30 bpm, then also you will be able to show it as IHB. Now we will have WHO classification indication also, so we will put it yes. Now let us try to understand what are the different like blocks that we will put to showcase all these specifications. So if we try to understand from beginning, okay, so let us say we will have to put one of the microcontroller. Okay, so that will be my MCU. Okay, so this MCU will be the main controller to control almost everything. Okay, now we need power supplies. So let us say we have a battery. Okay, so this is my battery. Let us say we have one USB connection also. Okay, and if you want, you can give one power jack also. Okay, now we'll have here switch application. Okay, so using MOSFETs or using some switching application, we'll try to connect all the three here. Okay, and these, I mean, based on the applications, So right now I'll suggest you can discard this jack. We will have just like battery as well as the USB connection. Okay. Now this is going to give us some output voltage which will be, let's say 6 volt or 5 volt based on the USB and battery. So battery will be giving 6 volt and USB will be giving 5 volt. However, battery will start draining, so that will be the voltage will get lower also. Okay. Now for microcontroller we require 3.3 volt capacity. So for that I will try to use one LDO, that is linear regulator, with 3.3 volt output. Okay. We'll give specifications of all of them later on. We'll just define what are the different blocks that will be required. Okay. If you have lower voltage and you need little bit high voltage for your air pump and the air valve, then for that you can use one boost regulator also. Okay. So boost regulator can give us 6 volt if you have an input of 5 volt, right? So this is how we'll try to use. So this you have to think of like how to use it, or otherwise you can discard this as well. Okay. Good. So we have made ourselves how we can design the power supplies. Okay. Now coming to the fact that we will have one air pump. Okay. Air pump. Okay. So in that, this will be the pump, this will be the motor that will be working. So for that we will have one connection through the connector. Okay. So this will be driven through my PWM signal. Okay. So this PWM signal will be switching this air pump off and on, because we will be giving one switching circuit here. Okay. Now this air pump is going to get connected through the cuff that is connected to the arm. Okay. This is how it is going to work. One more PWM will be working for my air valve as well. Okay. So air valve actually give us an opportunity to get open and close. Okay. So once it opens up, the air pump has inflated the cuff and it will deflate them, right? It will allow the air to pass out. Okay. So this is how it works. So this air cuff will be connected to the air valve as well. Okay. Now the best thing that we have to do is, this air cuff will be having an option to connect through the pressure sensor. Okay. So this pressure sensor can be analog type or digital type. So if you want to have high end design, then you can use digital type also, so you don't have to work on the ADC's control and everything. But right now we'll put it through the signal conditioning circuit. Okay, where we'll try to filter the output as well as try to utilize some of the instrumentation amplifier, amplification and everything, and we will have NIBP ranges also. So for that we'll send it to ADCs. Okay. So this is how we have designed the pressure sensor control technology also. Okay. Now we'll have some indication. Let us say we want to have buzzers for some alarms and error indications. Okay. So beep buzzers will be connected. So this will be also driven through some PWM signal. So we'll have magnetic transducers. Let us say you can utilize one of the part, very good part that we have always used, CS951AP. Okay, which is from CUI devices. Okay. Now we'll have some of the LEDs. Okay, so LEDs can be connected from the microcontroller directly, which will be indicating this that things are okay, like there is no error. So error indication will be through LEDs or even alarm and everything. At the same time we'll have power indication also at the output. So here we can connect one of the LEDs that power is connected. Okay. Now we'll have keys. Okay. So keys will be for different purpose. Let's say we have a start, a stop, like on off button. Then we'll have user key. We'll have some other mode key and all those things. So there will be some 3-4 keys that will be available. Okay. Then we'll try to use one LCD. Okay. So this LCD will be giving the output like systolic pressure, diastolic pressure and the pulse rate. Okay. So this will be backed by one backlight also. Okay. So we'll try to design a circuit of backlight which will be lighting this up or powering this up. All right, and we will have separate ADCs for like voltage monitoring for the 3.3 level or 6 volt level, as well as the input voltage level. So if this battery voltage directly is being measured, okay, if this battery voltage input is directly measured through the ADC, then it can be very accurately monitored, like what is the battery voltage level, and that can be also taken up. Okay, so alright guys, all these things can be there. Now what we'll do is we'll just make space little here, and so voltage monitor will write here. Now what are the different particular features that we can give in this? Okay, so we can give some Bluetooth functionality. Okay, also we will have one UART to USB connection. Okay, so UART to USB bridge, so this way it can be sent, the data can be sent directly to the PC also. Okay, so UART to USB connection will give, we will have Bluetooth connections. So this is how we will have complete set of the block diagram that we have used for our NIBP monitoring design. Alright, so if you do have any questions regarding any blocks or something like that, please put down your questions in the comment box, and we shall be able to answer you out in a particular very detailed fashion. Okay, so one of the device that you can follow always is a reference is given from Renesas. So Renesas has internal layout. So all these internal layout you can see, air valve is there, that is solenoid valve, main board is this one. We have buzzers, we have LCD, we have cuff connector, we have pressure sensors. Okay, we have a lot of other things. Let's say digital pressure sensor is also there. We have power indicator, we have switches, that 4 set of switches for different functionality like a start, stop. We have USB connector connectors, we have power connectors. Okay, we have air pump motor, this motor is there which is going to be having air pump capabilities. So this is how the complete set is given by the reference in the Renesas. So you can try to follow Renesas as well. However, this complete set of connections through the block diagram is enough for complete design. Alright guys, thank you.